Okay, today I'm gonna start chapter 5. I'm sorry if my voice is bad because I'm kind of sick. I got a cold, but I still have to do this. So chapter 5 is about integrals, but we're gonna start integrals first with area and distances in 5.1. Let's start with an example. So if you have a train that's moving along a track at a constant speed of 85 miles an hour, so this is the velocity and this is the time t. And if the train is moving at a speed of 85 miles per hour, so this is 25, 50, 75, between 7 a.m. and 11 a.m. So the speed is constant, that's v of t. The distance traveled by the train, as we know, since it's the speed is distance traveled between 7 a.m. 4 a.m. 11 a.m. that's 4 hours. So distance equals velocity times time, and that distance traveled is 340 miles. But assuming the train has a constant speed, but we trains don't have a constant speed. So instead of having a line for the speed, it'll probably be like this. Okay, so basically what we did with the speed, we found the area of this rectangle, and that was the distance traveled. But in the case of train that goes fast, slow, fast, slow, they stop, and so on, we're gonna find an area under a curve. Okay, that's why area and distances. Okay, so how do we find that? Well, we're gonna do some estimates first. So we're gonna talk about three methods for estimating areas under a curve. Three methods for estimating areas under a curve. The first one is using the left endpoints. I'll explain each one of them. The left endpoints. This comes to be using lower sums. And then using the right endpoints. Which is gonna come up to upper sums. And then using the midpoint method, which uses the average sums. The average sums. Here's an example, okay? So if I say estimate the area under the curve, f of x equals x squared over the interval 1 to 5, using the first method is left endpoints and 4 subintervals. So basically what we're gonna do, because we have a curve, so it's not a train that's going at a constant speed. It's a train that's going at different speeds over a certain time period. So y equals x squared between 1 and 5. At 1, let's say this is 5, 10, 15, 20, 25. So at 1, it's 1. At 2, it's 4. At 5, it's 25, 5 squared. So basically, we want to find the area under this curve, but we want to do estimate using rectangles, okay? And to do that, we're going to divide the interval from 1 to 5 to 4 subintervals. So we want, so this is from 5 to 4, there is 4 units, so divided equally. So we take 5 minus 1, that's how we get the 4, divided over 4 subintervals. Each subinterval is 1 unit, okay? So we're gonna take each subinterval as 1 unit, and we're gonna use the left endpoint as the height of the triangle. So left endpoint, so that's gonna be the first triangle, the area, that's gonna be the second triangle, the third triangle, that's what left endpoint means. So we are underestimating in this case because we're leaving these gaps. So the area under the curve equals the area of the first triangle, which is 1 times f of 1, plus the width of the second triangle, 1 times f of 2, right? 1 times f of 2, plus 1 times f of 3, plus 1 times f of 4. So f of 1 is 1, f of 2 is 4, because 2 squared is 4, 3 squared is 9. Remember, f of x is x squared. And 4 squared is 16, so square units. So this is an underestimate, right? This uses what we call, these are called lower sums. So now let's do the upper sums. Let's do an overestimate. So using a right endpoint, number 2. Using right endpoints. So I'm not gonna rewrite everything. It's all in the notes. So what we're gonna do is we're gonna have, so from 1 to 2, we're gonna use 2 at the height of the rectangle. So you can see we're overestimating. This is the first rectangle. This is the area of the second rectangle, the third rectangle, and the fourth rectangle. And we are getting upper sums, and we get an overestimate of the actual area, okay? Because we're adding these shapes, these areas. So it will be, so the area is 1 times f of 2 plus 1 times f of 3, right? 1 times f of 2, 1 times f of 3 plus 1 times f of 4 plus 1 times f of 5. F of 2 is 4, that's 9, 16, 25, 54 square units. Now we know the area under the curve is somewhere between the lower sums and the upper sums. To get a better estimate than these two, we use the midpoints, the third one, using midpoints instead of left endpoints or right endpoints. So the midpoint of 1 and 2 is 1.5. So basically it's getting too crowded, but it's okay. So we're getting 1.5, 2.5, 3.5, 4.5. So we're doing 1.5, so you can see, and then 2.5. So it's overestimate and then underestimate. They balance each other out. So it's 1. So it's 1 times f of 1.5 plus 1 times f of 2.5 plus 1 times f of 3.5 plus 1 times f of 4.5. So if we put that in our calculators, we get 41, which is somewhere between 30 and 54. It's a better estimate than either one of them. Okay, so this is just an example. Now we're going to talk about the general case. Now we're going to talk about the general case, upper and lower sums. Again, I'm not going to write down everything that's in the notes. You can just add the notes. They're all in there. So we're given a function y equals f of x over an interval ab, a continuous function over a closed interval. Now we're going to divide the interval ab, divide it just like we did between 1 and 5, into n equal subintervals. So the width of each subinterval, is the width of the whole interval divided by the number of intervals that we want, number of intervals. Just like we did in the example we had, b minus a over n, okay, where n was 4 in that case. Okay, and then we're gonna say this is x0, the first one, and then x1. Remember, this is called delta x, so x1 is a plus delta x, and then the second one is x2, a 2 delta x, so we keep in delta x because they're equally spaced, and then x3 is a plus 3 delta x, so xi is a plus I delta x, and xn equals b. Okay, so if you take each subinterval, on each subinterval, like x0, x1, the function is continuous and the interval is closed. That means there's a maximum and a minimum on each subinterval. So there's f of little mi and f of mi on each subinterval. This is gonna be the minimum, and this is gonna be the maximum, thanks to the p-value theorem. So if you take the minimum, which is which is the height of the rectangle, and times it by the width of the rectangle, which is delta x, that gives you the area of the rectangle. That's gonna be less or equal f of mi. Why is that? Because this is the smaller value, this is the bigger value. It makes a lot of sense. This is called inscribed rectangle, this is called circumscribed rectangle. If you add them all up, if you sum all these inscribed rectangles, this is called lower sum. And if you add up all these circumscribed rectangles, you get what we call upper sum. And of course, you're going from 1 to n. So the area is somewhere between the lower sum. This is exactly what we did in the example, it's just more general here, and the upper sum. Lower sum and the upper sum. Okay, so now we can define the area of a region. So remember, when we talk about area is the area of a region in a plane Okay, let f be a continuous and non-negative. So it's extremely important to have continuity, and the graph has to be above the x-axis, okay? Continuous and non-negative over AB. Otherwise, you can't find area. The area of the region bounded by the graph of f, bounded by the graph of f, the x-axis over the AB is the sum of f of ci delta x. Remember, lower sum, upper sum, I use ci because it could be any ci. And then by going to the limit, we want to make the intervals as small as possible, so the number of them has to be as large as possible, because when you're finding area under a curve, the smaller the rectangles, the better the approximation, okay? That means n has to be infinite. And f of ci, you can use left endpoint, right endpoint, or any point, but for simplicity, we're gonna use, just for simplicity, use ci a plus I delta x with right endpoint, I equals 1 to 1. Just for simplicity, okay? It doesn't matter. And there's example on page 5. It's just very similar to the parabola I did. So please go over that, okay? I don't think I need to go over that. It's very similar. I'd rather do something different, okay? So that's for you to look at. Just go over that, page 5. Now on page 6, number 10, page 382. Number 10, page 382. Let's see what's in there. It says, the table shows speedometer readings at 10-second intervals during a 1-minute period for a car racing at the Daytona International Speedway in Florida. Estimate the distance the race car traveled during this time period using the velocities at the beginning of the time intervals. So they want the distance, and they're talking about 10-second intervals. Remember, 10-second is 10 over 3600, which is 1 over 360 of an hour. Okay? So they want the distance traveled, the distance the race car traveled during this time period using the velocities at the beginning of the time intervals. So distance, we have the time and we have the velocity. So the time is 1 over 360 times each velocity. We're given the velocities 182.9 plus 168 plus 106.6 99.8 plus 20.5 plus 176.1. Instead of doing 1 over 360 times this, 1 over 360 times that, I pulled that out. Remember, distance is time times velocity for each one of them, okay? And if you put that in your calculators, the distance traveled during that time period is 2.383 miles. Okay, part B. Give another estimate using the velocities at the end of the time periods. At the end of the time periods. So we did left endpoint. Now we're gonna do right endpoint. This was left endpoint. Now we're gonna do right endpoint basically. So distance is 1 over 360. Instead of starting at 182.9, we're going to start at 168. And instead of stopping at 176.1, we have to start 175.6. That 106.6 plus 99.8, 24.5 plus 176. You see, we stopped because that was the left endpoint. Now we're going to go to the right endpoint, which is 175.6. And this is roughly 2.363 miles. Are your estimates in parts of A and B upper and lower estimates? Explain. Are they? Well, they're neither, because the velocity is not increasing all the time. Because to have upper or lower, your graph has to be increasing or decreasing all the time. This doesn't look like it because you can see the velocity is 182.9, then 168, then 106, so it keeps fluctuating. So it's neither. Okay, it's neither upper nor lower. Because you can see it decreases, decreases, increases, increases. Okay, so it can be. All right, let's look at another one of those, number 18, page 383. 383. It says, use definition 2 to find an expression for the area of the graph of f limit. Do not evaluate the limit. So f of x equals x plus ln of x. X is between 3 and 8, so they want an expression for finding the area. Remember, the area is the limit as n goes to infinity. Sum I equals 1 to n f of ci delta x. So we gotta find all these values. So delta x is b minus a over n, which is 5 over n. Ci is a plus I delta x. A is 3, I is I, and delta x is 5 over n. So 3 plus 5i over n. F of ci is f of 3 plus 5i over n, which we're going to plug in there. 3 plus 5i over n plus ln 3 plus 5i over n. So we're going to take all this and put it in there for f of ci, and this put it in there for delta x to get the area, and sum from 1 to n. F of ci, 3 plus 5i over n, plus ln of 3 plus 5i over n. All this times delta x is 5 over n. This is an expression. We are not here to evaluate it, just put the expression down. That's all they asked. And that was an introduction for chapter 5. 5.1 is done. We will see you in 5.2 shortly.